Hi everyone. In this video, we are going to discuss about stub matching and types of stub matching. That is single stub matching and double stub matching. First, we are going to discuss about stub matching. What is a stub matching? A stub is a piece of transmission line. Stub is a piece of transmission line. A section of transmission line can be used as a matched section by inserting them between source and the load. The transmission line, and this is the source end and this is the load end. A section of transmission line can be used as a matched section by inserting them source and the load. To connect sections of open circuited or short circuited transmission line is known as stub or tuning stub. And it is connected with the main transmission line at a point from at a distance from loaded. The matching with the help of the stub or tuning stub is called as a stub matching. The important properties of the stub matching are the length and characteristic impedance remains unchanged. The characteristic impedance and the length of the transmission lines remains unchanged. And the second property is mathematically it is possible to add adjustable susceptance in sync with the main transmission line. So these two are the properties of the stub matching. What are the properties? The length and characteristics of the transmission line remains unchanged. Mathematically, it is possible to add adjustable susceptance in shunt with the main transmission line. Basically, there are two types of stub matching, that are single stub matching and double stub matching. Single stub matching and double stub matching. First, we are going to discuss about single stub matching. Single stub matching. A type of transmission line is frequently represented by a single stub matching, as shown in figure. So this is the figure of the single. A type of the transmission line is frequently employed or frequently represented for single stub matching. The principal element of this transformer is a short-circuited section of the transmission line, whose open end is connected to the main transmission line at a particular distance from the load, whose open end is connected to the main transmission line at a particular distance from the load, where the input conductance is equal to the characteristic conductance of the main transmission line at that point, and the stub length is adjusted to provide the susceptance which is equal in value but opposite in sign to the input susceptance at the point of the attachment. So the total susceptance at the point of the attachment should be 0. The total susceptance at the point of attachment is 0. So that is the single stub matching. The mathematical relations for the location of the stub and the length of the short-circuited stub can be started from the input impedance of a transmission line. So we know that the input impedance of a transmission line is given by Zs is equal to Z0 into Zs is equal to Z0 into Zr plus JZ0 tan HPL plus Z0 plus Zr tan HPL, where Zs is the input impedance of a transmission line, Z0 is the characteristic impedance of a transmission line, Zr is the load impedance of a transmission line. Now converting the impedances into admittances. Now converting impedances into admittance. So by putting Y0 is the characteristic admittance. The characteristic admittance is reciprocal of the characteristic impedance. Ys is the Yr is the load admittance, which is reciprocal of the load impedance. Ys is the input admittance, which is the reciprocal of the input impedance Zs. So what is the character? What is the input impedance of the transmission line? Zs is equal to Z0 into Zr plus Z0 tan HPL by Z0 plus Zr tan HPL. That is the equation of the input impedance of the transmission line. So converting that impedance into admittance. How to convert? Using the input impedance is reciprocal of the input admittance is reciprocal of the input impedance. So using that expression, find out input admittance value. So therefore, we get Ys is equal to 1 by Z0, Ys is equal to 1 by Z0, 1 by Zs, where Zs is Z0 into Zr plus Z0 tan HPL plus by Z0 plus Zr tan HPL. And this denominator term is coming to the numerator. We get input admittance Ys is equal to 1 by Z0 into Z0 plus Zr tan HPL by Zr plus Z0 tan HPL. 1 by Z0 is the characteristic admittance Y0. So therefore, Ys is equal to Y0 into Z0 is 1 by Y0 and Zr is 1 by Yr. So therefore, Ys is equal to Y0 into 1 by Y0 plus 1 by Yr tan HPL by 1 by Yr plus 1 by Y0 tan HPL. Take the LCM. LCM is Y0 and Yr, and after taking the LCM, numerator and denominator, Y0, Yr is cancelled. So we get Ys is equal to Y0 into Yr plus Y0 tan HPL by Y0 plus Yr tan HPL. For high frequency transmission line, the attenuation constant becomes 0. Alpha is equal to 0. Alpha is equal to 0, then the propagation constant is purely imaginary. That is P is equal to J beta. So that applying this condition into above expression, we get the input admittance Ys is equal Y0 into Yr plus Y0 tan H J beta L by Y0 plus Yr tan H J beta L. Since tan H J beta L is equal J tan beta L, applying this condition into above expression, we get input admittance Ys is equal Y0 into Yr plus J Y0 tan beta L by Y0 plus J Yr tan beta L. Using normalized admittances. So what is the normalized admittances? And what is the normalized impedances? The normalized impedance is defined as the ratio of the load impedance to characteristic impedance. That is normalized load impedance. And normalized input admittance is input impedance by characteristic impedance. That is normalized impedances. Now here using normalized admittances. Admittance is the reciprocal of the impedance. So using normalized admittances, y suffix small s is equal y suffix capital S by y0. Y suffix small s is the normalized input admittance. Y suffix capital S is the input admittance. Y0 is the characteristic admittance. So the normalized input admittance is given by input admittance divided by characteristic admittance. So similarly, normalized load admittance y suffix small r is equal y suffix capital R by y0. Y suffix small r is the normalized load admittance, y suffix capital R is the load admittance, y0 is the characteristic admittance, and it is given by y suffix small r is equal y suffix capital R by y0. So that is normalized admittance concept. Therefore, from the above equation means input admittance equation, and RHS side y0 is coming to the LHS side, we get ys by y naught is equal ys by y naught, or otherwise, and in this equation, dividing on both sides by y naught. So dividing on both sides by y naught. So we get ys by y naught is equal y naught by y naught. Hence it. Ys by y naught. So that is another way. In that equation, that is another way. And RHS side y naught is coming to the LHS side. We get ys by y naught is equal yr plus j y naught tan beta l by y naught plus j yr tan beta l on RHS side, and take the common y naught. We get ys by y naught is equal y naught by yr by y naught plus j tan beta l by 1 plus j yr by y naught tan beta l. So now in the numerator and denominator, take the common y naught. That y naught is cancelled. So we get this is the resultant expression. So what is ys by y naught? Ys by y naught is the normalized input impedance that is represented by y suffix small s. Yr by y naught is the normalized load admittance that is indicated by y suffix small r. So therefore, the normalized input admittance y suffix small r is equal yr plus j tan beta l by 1 plus j yr tan beta l, where beta is the phase shift constant and length is the L is the length of the transmission line. So this equation for normalized input impedance. So using rationalization, ys is equal yr plus j tan beta l by 1 plus j yr tan beta l. Using rationalization or multiplying numerator and denominator by 1 minus j yr tan beta l, we get this is the expression. Multiplying numerator and denominator, multiplying yr plus j tan beta l into 1 minus j yr tan beta l, and the same time multiplying the denominator factors 1 plus j yr tan beta l into 1 minus j yr tan beta l. Okay, yr into 1, yr minus j yr square tan beta l, j tan beta l minus j square yr tan square beta l. So j square value is minus 1 minus into minus plus yr tan square beta l divided by denominator factor is a plus b into a minus b. A plus b into a minus b, a square minus b square. So we get 1 square minus j yr tan beta l whole square. J square value is minus 1. So before minus is there, minus into minus plus. So therefore, the normalized input impedance ys is equal. Now here, in this term, yr is the common, and separately arranging the real parts and imaginary part. So in the numerator, first term and fourth term, take the common yr into 1 plus tan square beta l plus j, and second term and third term, take the common j tan beta l into 1 minus yr square by 1 plus yr square tan square beta l. So that equation may be separately arranging real parts and imaginary part. We get ys is equal to yr into 1 plus tan square beta l by 1 plus yr square tan square beta l plus j tan beta l into 1 minus yr square by 1 plus yr square tan square beta l. Impedance is a complex quantity. What is the impedance? Complex quantity, that is r plus jx, where r is the resistance and x is the reactance. And similarly, the admittance is also a complex quantity, which is the conductance and susceptance. G plus JB. G is the conductance and B is the susceptance. Now here the normalized input admittance. So ys is equal G suffix s plus j into B suffix s, where G suffix s is the input conductance and B suffix s is the input susceptance. In the above equation, equating and real parts and imaginary part. So Gs is the real part of the admittance, Bs is the real part of the imaginary part of the admittance. Equating real term and imaginary terms, we get the input conductance Gs is equal yr into 1 plus tan square beta l by 1 plus yr square tan square beta l, And equating imaginary terms on both sides, we get input susceptance Bs is equal tan beta L into 1 minus yr square by 1 plus yr square tan square beta L. But for the no reflections, the condition for the no reflections, the normalized admittance Ys is equal to 1. But Ys is equal to Gs plus J into Bs, equating on both sides real parts and imaginary part. Gs is equal to 1 and Bs is equal to 0. Okay, but for no reflection cases. What is the length of this stub? What is the length of the transmission line? Small l is the length of this transmission line. Thus, the stub has to be connected where there is no reflections. So that stub is connected from the load end of the transmission line at a distance from LS. Stub is connected from the load end of the transmission line. The length is LS. L is the length of the section of the short circuited stub length. L suffix S is the short circuited stub length. And applying this condition into above expression, applying this condition and this condition, no reflections conditions into above expression, we get input conductance Gs is equal to 1. Real part of the admittance Ys is equal to Gs is equal to, that is the equation. Applying this condition and no reflection conditions into input conductance expression, we get Gs is equal to 1, that is equal to RHS term. Yr into 1 plus tan square beta, L is equal to Ls. Ls is the length of the short circuited stub. By 1 plus yr square tan square beta Ls. So take the cross multiplication, we get 1 plus yr square tan square beta Ls is equal, multiplying yr within the bracket term, yr plus yr tan square beta Ls, that is equal yr tan square beta L tan square beta Ls minus yr tan square beta, this yr tan square beta Ls is coming to the LHS side, we have minus yr tan square beta Ls, yr plus 1 is going to the RHS side, we have minus 1. On LHS side, for both the terms, take the common, yr tan square beta Ls into yr minus yr is equal to yr minus yn. On both sides, yr minus 1 is cancelled, we get yr tan square beta Ls is equal to 1. So yr is going to the RHS side, we get 1 by r, 1 by yr. So therefore, tan square beta Ls is equal to 1 by yr. Tan square beta Ls. What is yr? Normalized load admittance. What is the normalized load admittance? Yr by y0. So 1 by yr is y0 by yr. Tan beta Ls is equal to square root of y0 by yr from this expression. Therefore, beta Ls is equal to tan inverse of square root of y0 by yr, and Ls is equal to 1 by beta into tan inverse of y0 by yr. Where beta is the phase shift constant, the phase shift constant beta is equal to 2 pi by lambda, and this is the length of the short circuited stub in terms of admittance. Similarly, in terms of impedance, Ls is equal to 1 by beta into tan inverse of square root of zeta by zeta. This equation gives the location of the stub from the loaded. Now the susceptance at the point of the attachment. Is given by, what is the susceptance? That is the imaginary part of the admittance. So what is that value? Bs is equal to Bs is equal to tan beta L into 1 minus yr square by 1 plus yr square tan square beta L. So this is the input susceptance, that is the imaginary part. So from this expression, Bs by y0 is equal tan beta ls. What is the tan beta ls? Square root of y naught by yr into 1 minus tan square beta ls. Yr square by y naught square by 1 plus yr square by y naught square into y naught yr. Applying and substitute tan beta ls and tan square beta ls values into bs expression, imaginary part of the admittance expression. This is the expression. So that is equal. Here take the LCM y naught square minus y square by y naught square. At the same time in the denominator take the LCM. Okay. Here in the denominator factor yr is the cancel, y naught is the cancel, and the remaining term is yr by y naught. And take the LCM in the denominator y naught plus yr by y naught. And reducing we get the resultant expression bs by y naught is equal and bs is equal square root of y naught by yr into y naught minus yr. Simplifying that calculation part, finally we get the susceptance, input susceptance bs is equal square root of y naught by yr into y naught minus yr. So this is the equation for input susceptance. This is the equation for input susceptance. So the short circuited impedance is Zt is equal Vs by Is, that is equal Z0 into tan beta Lt. The impedance of the short circuited transmission line already calculated, already derived in previous classes. So that is Z0 tan beta L. So now here the L is equal to Lt, Zt is equal Vs by Is is equal Z0 tan beta Lt. And the short circuited admittance, that is the impedance case. Similarly, in admittance case, yt is equal to 1 by jt, that is equal minus jy naught cot beta lt. And the admittance is a complex quantity, that is g plus jb. So therefore, yt is equal gt plus jbt, equating real parts and imaginary parts on both sides. We get gt is equal to 0 and bt is equal, b suffix t is equal to minus jy naught cot beta lt, where L suffix t is the length of the short circuited stub. Ls is the location of the stub, short circuited stub, and Lt is the length of the short circuited stub. Now at the point of the attachment, the sum of the line susceptance and the stub susceptance must be 0. Now at the point of the attachment, the sum of the line susceptance and the stub susceptance must be 0. So that is Bs plus Bt is equal to 0. What is Bs value? Already calculated. That is square root of y naught by yr into y naught plus yr. And what is the Bt value? Minus y naught cot beta Lt. So plus into minus is equal to 0. And reducing this equation, we get cot beta Lt is equal to square root of y naught by yr into y naught minus yr by y naught. Here y naught is written as square root of y naught into y naught. Numerator and denominator, one square root of y naught is cancelled, and the remaining term cot beta Lt is equal y naught minus yr by square root of y naught yr. And this is the cot beta L value, and tan beta Lt is 1 by cot beta Lt, that is equal square root of y naught yr by y naught minus yr. Beta Lt is equal tan inverse of RHS term, and Lt is equal 1 by beta into tan inverse of square root of y naught yr by y naught minus yr. Lt is equal to 1 by beta into tan inverse of, and this is the equation of the length of the short circuited terms in terms of admittance. Similarly, in terms of impedance, Lt is equal to 1 by beta tan inverse of square root of z0 zr by zr minus z0, where beta is the phase shift constant, that is 2 pi by lambda. This is the equation of the length of the short circuited stub required. Stub matching almost invariably used at fairly higher frequencies, that is in standing wave ranges of broadcast band.